Hello everyone, myself Himanshu Mittal, a member of Group 8, is presenting today a class of algorithms called the trust region methods. Generally, we use a vanilla policy gradient methods which are used in continuous action spaces settings in which the action space are continuous in nature. So these policy gradients are generally very unstable as they do unstable updates during training and thus can break the policy and leads to poor performance. So stabilizing these policy gradients are very crucial. So even if once a bad policy is learned by anyhow, since they are noisy updates, it generates a very low quality training data and thus the overall training collapses. So choosing the learning rates is very crucial and it's significantly harder. So here we have to stabilize these updates while training to maintain the performance and for efficient learning. So for that, there are improvement on the on the simple Valina policy gradients. These are TRPO algorithm, which is the trust region policy optimization algorithm, and ACKTR algorithm, which is actor critic chronometer trust region algorithm. These approaches aim to prevent drastic changes in the policy during training by using trust regions and monitoring KL divergence. Basically, they introduces a regularizing term in their objective function, which is generally a penalty to so that the policy does not change drastically between the new policy and the old policy which it was before. So we studied these policies and then we conducted our experiments on the following four environments, two for TRPO, which is MuJoco and PyBullet simulators, and the other half Cheetah and V4 for the other algorithm. So here we compare these two algorithms and discuss their results. So let's focus on the first algorithm, which is the TRPO, that is the Trust Region Policy Optimization. So from the algorithm itself, we can see that there is a term called trust region. Here, a trust region is defined in a parameterized space of the policy in which a policy is acceptable only if it lies in that trust region of the previous policy, or it lies in the region which is close to that previous policy which was trained for. So let's see in detail. So why do we need such policy? So as I told, there is a lot of limitations in the naive or vanilla policy gradients, which is the first one is clearly that it is very hard to choose the step sizes, as bad step is much more damaging since it affects the vegetation distribution. As we know that we after updating the policy, the samples are clearly from a completely different distribution as before. So if by any chance we got into the wrong distribution, there is no way to recover from that wrong distribution, thus we will continue to learn the bad policy. And the second most disadvantageous part is the lack of sample efficiency, as there is only one gradient step per environment sample. So, what is the algorithm which kind of overcomes these objectives, these limitations of the vanilla policy gradients? So, the first step is clearly the called the discounted visitation frequency, in which we focuses on how to get access to all the samples from the all the distributions which were used in the trainings. So here TRPO starts by defining the distribution like this, where probabilities of the previous state and from the next states all contribute with a factor of gamma to the training, instead of being discarded after the first iteration itself. This gives more weights to the states that are encountered early and often as well. Next, we try to we change the objective function here and we regularize it using the KL divergence term. Here, the objective function is shown clearly, in which the loss function is equals to eta pi uh, plus the summation of rho pi s, which was defined earlier. And next there is this is the same term as we have used in the DQN networks. Instead of that, we use the advantage term here. And the eta pi is similar to a target which we are used to in the DQN networks. The objective here estimates is how good the new policy would be, assuming it behaves similarly to the old one. So for that, we introduce a trust region constraint. So here we use the KL divergence metric, and we introduce a constraint such that the KL divergence of the previous policy is of the new policy and the previous policy should be less than a certain threshold called delta for safe updates, since we don't want updates to be drastically different from the previous updates. uh, i- so the final objective function here becomes in an equivalent sense that we have to maximize on theta the expectation of pi theta for action probability of pi theta action given the state st divided by the pi theta old probability of action given as state st into the advantage matrix. But this objective is constrained to the expectation of the KL divergence of the old policy with the new policy, and which should be less than a small threshold called delta. So due to the presence of this scale divergence, we can also use the Lagrangian here to get give a more simplified form of the objective function, where which using the Lagrange multipliers we have given a penalty to the actual objective function, which is like that. So instead TRPO now faces a problem in that we cannot use standard gradient descent techniques in this objective function. We cannot use just simple gradient of this and then we iterate it using SGD. For that we have to use new techniques which are more advanced approach, which are conjugate gradient methods and backtracking line search. In the conjugate gradient method, we generally approximate the gradient direction by using a linear system in which Fisher matrix is involved. Fisher information matrix is involved. So it allows TRPO to determine an appropriate update direction. For backtracking line search, once a direction is identified in this, TRPO perform a backtrack to select a suitable step size and then ensures that the updated policy remains within the predefined care divergence. So here, even if the TRPO, we can see that even if we remove the constraint, we can see the connection of the TRPO with the other algorithms which we have already learned. If we remove the constraint of the KL divergence, it just simply becomes a policy iteration algorithm, which is not visible right now, but it it becomes like that. And secondly, if Euclidean regularization metric or the Euclidean distance is used instead of the KL divergence, which is also a distance metric, then we get back the vanilla policy gradient algorithms. So here are some limitations in the TRPO, as the TRPO algorithm relies on the second order optimization, as we have to calculate the Fisher information matrix and the KL divergence gradients, which are which are computationally very expensive, and the training time is just increased. So these are the limitations for the TRPO algorithm, thus require advanced implementation techniques.
We now observe the results for both the half cheetah and the ant environment in Pybolid and Mojoko simulators, respectively. The left graphs show the rewards obtained during the training set, and the right graphs shows the test rewards. Similarly, we could see the graphs for the ant environment. From these graphs, we observe that TRPO achieves the highest reward among all methods in the half cheetah environment using Mujoko. Hence, we could conclude that it is effective in stable and structured environments. Similarly, we also observed that it struggled in the AND environments on both Mujoko and Bullet, achieving relatively low rewards. This indicates poor performance in environments involving higher complexity. We also see a strong stability in simpler tasks, like in the half cheetah environment that was not shown in the ant environment. Hence, we could conclude that it is stable in simpler tasks but lacks the adaptability it requires to perform well in dynamic or high dimensional tasks. Similarly, performance differences can be observed in both the environments. Hence, the effectiveness could be influenced by the simulator. We also observe that it performs slightly better with Mojoko, which has more accurate physics modeling. Lastly, we could conclude that the pi bullet version of half cheetah TRPO performed competitively with the PPO algorithm. Hence, we could state that it has a good stability.
Let's look at actor, that is actor critic using Kronecker factored trust reason. So what is actor? It is a policy gradient method, but unlike basic approaches such as reinforce or E2C, it constrains policy updates to stay within a trust region. This prevents the policy from changing too abruptly, which makes learning more stable. Think of it as taking safe, measured steps toward better policies. Architecturally, it uses an actor critic structure just like E2C. The actor selects actions while the critic evaluates them. It's like having a player and a coach. The player explores and the coach tells how good the move was. And it has one deep network to estimate the policy and another to estimate the advantage function, which we'll look later. Now, why do we need actor when we already have TRPO? So TRPO is computationally expensive because it requires computing the FIM, that is Fisher inversion matrix, which scales poorly with the size of network, making it infeasible for large deep networks. Actor speeds up this optimization by reducing the complexity of calculating the inversion of the FIM using Kronecker factor approximation. And this approximation is used to optimize both actor and critic. Now, actor maintains a running average of the curvature, and so it doesn't waste compute recalculating everything each step. This running estimate smooths out any fluctuations and keeps training efficient and more stable. And thus, the per update cost of actor is only 10% to 25% higher than SGD. Now, Kronecker factor approximate curvature. Second order optimization is more accurate, but it increases the complexity, which usually cannot be justified for its return compared with the first order optimization, even in RL. Now, this second order derivatives, it requires you to invert a Hessian matrix which is in the order of n square, and so this is not feasible for larger deep network models. KFAC approximates the inversion of FIM and computes the parameter updates one network layer at a time. and each calculation only involves the nodes in a layer instead of all the nodes in the whole model, and therefore the computational complexity drops significantly. Now let's look at some notation which we will use throughout the presentation. So let P y given x denote the output distribution of a neural network, and L denotes the log likelihood. W is the weight matrix in the Lth layer, where C out and C in are the number of output and input neurons of the layer respectively. The input activation vector to the layer is denoted by alpha, and the pre-activation vector for the next layer is computed as S equals to W dot A. Now, KFAC calculates the derivative of L relative to model parameters W in a deep network layer instead of the whole model. So, after applying the chain rule, the partial derivative of L relative to the parameters W in a layer becomes gradient with respect to W, gradient of L with respect to W equals to gradient of L with respect to S dot A transpose, and F can be calculated using this expression, and so the corresponding calculation for each layer becomes FL. And after applying the partial derivatives, after applying this derivative, we can simplify the calculation as this. Here A denotes expectation of A transpose, and S denotes the expectation of this value. Now we can apply P cross Q inverse equals to P inverse cross Q inverse, and P cross Q into vector T equals to PT into Q transpose dot Q transpose, and so the updates to W for each layer becomes this. And so to compute the parameters changes for each layer, we only need to find the inverse of A and S. We update the network layer by layer, and each calculation involves nodes in a single layer only. Now, how is this useful? So consider the number of nodes in each layer is in thousand or hundred of ranges rather than millions for the whole network. So this is much manageable, and thus KFX significantly reduces the computational complexity. In TRPO, the variance in computing F is high, and so to improve accuracy, many samples are collected in calculating F. KFAC, since it maintains running averages for the expectations A and S in the approximation, it reduces variance, and therefore it requires far fewer samples. Now critic. ACKTR uses a critic to estimate the advantage function. To train the model, we compare the model predictions with the target values and solve the problem as a least square problem. One common approach with second order algorithm is Gauss-Newton. If we compare the actor and the critic side by side, the equation are similar, and so the FIM is equivalent to the Gauss-Newton matrix in the critic, and hence we can apply similar k-fact approximation method to the critic and update each layer one by one to reduce the computational complexity. The following graph shows a performance improvement in applying the Gauss-Newton norm, which is a second order optimization rather than the usual Euclidean norm to the critic in actor. Now sample efficiency. So actor scores have a higher rewards and achieves a human level performance in fewer training episodes. This table shows the number of time steps executed per seconds, and the higher the number of time steps executed per second, the better is the algorithm, and actor achieves speed performance within 25% of A to C, which is a first order optimization. So uh, this graph, it shows the reward during training and the test reward for half cheetah on pi bullet. The left is the graph for during training, for the reward during training, and the right is the graph for reward during test. And this is a similar graph, but it is for musical environment. Overall, the actor method was very unstable in both environments, and it could be due to a lack of fine tuning of parameters or some bugs in the implementation. This concludes our presentation. Thank you.